You know, when most people hear the words organic chemistry, they immediately think of late nights, flashcards, and just memorizing tons and tons of reactions. But today, we're going to flip that on its head. We're not going to treat it like a textbook. We're going to see it for what it really is, a performance, a dance, with just a few simple rules that control every single move. So let's just ask ourselves this. What if we just threw out the flashcards for a minute and pictured a dance floor instead? What if figuring out how molecules react was as intuitive as learning the steps to a dance? Well, that's exactly what we're going to do. We're going to find the rhythm of organic chemistry. All right, you ready? Let's hit the dance floor. Every great dance has rules, right? A structure that all the performers follow. And on our chemical dance floor, there is one absolute star of the show. One performer whose every move dictates the entire performance. And this is it. This is the big secret. At the end of the day, every single reaction in organic chemistry is just a story about electrons. All we have to do is ask two simple questions. One, where are the electrons all bunched up right now? And two, where do they really want to go? That's it. That is the whole game. Okay, so how do we actually write this dance down on paper? We use this thing, the curved arrow. I want you to think of it like the choreographer's notes scribbled right onto the page. It's not just vaguely pointing from one molecule to another. No. It is showing the precise path that a pair of electrons takes as it flows from an area where there's a lot of them to an area where there aren't enough. This is our fundamental dance step. All right, so we know the basic move. Now it's time to meet the dancers. And, in chemistry, just like on any dance floor, you've got your natural leaders and your natural followers. Or maybe a better way to put it is you've got your givers and you've got your takers. So let's meet them. On the left, we've got the givers. Now, the technical term is nucleophiles, which just means nucleus-loving. All you need to remember is that they are loaded with electrons and they are looking to donate a pair. On the right, we have the takers, the electrophiles, or electron lovers. These guys are electron poor, and they are actively looking to accept a pair. The whole dance of chemistry is what happens when a giver finds a taker. So, how do we measure how willing a molecule is to be a giver? Specifically, how willing it is to give away a proton, which is kind of the classic acid-base dance move. Well, chemists have a number for that, and it's called pKa. And the rule is super simple, but it's a little counterintuitive at first. You kind of have to flip your brain a little bit. Okay, let's break this down real quick. A really strong acid gives away its proton easily, right? That means it has a big acid dissociation constant, or Ka. But here's the trick. pKa is the negative log of Ka. And if you remember your math, taking a negative log flips the relationship upside down. So here's the bottom line. The only thing you need to remember. A smaller pKa means a stronger acid. A tiny pKa means a very, very enthusiastic giver. Okay, we've met our dancers. We know how to size them up. Now for the action. Let's watch the actual moves they make, the forming and breaking of bonds. This is how dancers find new partners and leave their old ones behind. When two atoms in a bond, our dance partners, decide to part ways, they can do it in two main styles. First, you've got homolytic cleavage. Think of this as the nice, amicable split. They part ways, each partner takes one electron, and they go off on their own. But then, there's heterolytic cleavage. Oh, this is the drama. One partner just grabs both electrons from the bond and storms off, leaving the other one totally abandoned with a positive charge. And right after that breakup, you get these super high energy, totally unstable solo dancers called reaction intermediates. You've got the carbocation, which is electron poor, the carbanion, which is electron rich, and the radical, with that lonely unpaired electron. These guys are not stable, and they do not stay alone for long. They are frantically scanning the dance floor for a new partner. Now, not all of these solo dancers are equally unstable. Let's take that carbocation. Its stability completely depends on how many carbon neighbors it has. A tertiary one connected to 3 other carbons, is the most stable. Why? Well, it's because those neighbors can share a little bit of their electron density to help stabilize that positive charge. It's basically like having a bunch of friends rush over to support you when you're feeling down. More neighbors, more support, more stability. Okay, we've got the rules, we've met the dancers, and we've seen the basic moves. So let's put it all together and watch a featured performance. We're going to put a really common and versatile molecule right in the spotlight: alcohol. So what even is an alcohol? It's just an organic molecule that has a hydroxyl or OH group hanging off of it. But that one little group makes it an incredibly versatile dancer. It can act as a weak giver or an acid by donating that little proton. Or it can act as a weak taker, a base, by using the extra electrons on its oxygen. It can pretty much dance in any style. And because it's so versatile, alcohol has a whole repertoire of dance routines it can perform. It can do dehydration, oxidation, substitution, and I know you're looking at this and thinking, oh great, more reactions to memorize. But no, every single one of these is just a different sequence of those same basic steps we've already learned. It's all just a giver meeting a taker under different conditions. That's all it is. So we've seen how all these rules apply to one specific molecule, but here's the truly beautiful part of all this. The rules don't change. The dance floor gets bigger, the music changes, but those fundamental steps, they stay exactly the same for pretty much countless other molecules. Want to see what I mean? Let's bring another dancer onto the floor for a quick comparison. The carboxylic acid. Now, it looks kind of similar to an alcohol, right? It's also got that OH group. But a tiny little structural change makes a world of difference in how it performs on the dance floor. Okay, remember pKa, our handy measurement for how willing a molecule is to be a proton giver? For a typical alcohol, like ethanol, the pKa is around 16. On the grand scale of acids, that is really, really weak. It holds on to its proton very tightly. Now look at this. For acetic acid, a classic carboxylic acid, the pKa absolutely plummets to about 5. Whoa. Remember, a smaller pKa means a stronger acid. And that's not a small change. We're talking about a difference of roughly 100 billion times in acidity. So what in the world is going on here? The secret is what happens after it gives the proton away. That negative charge that's left behind isn't stuck on just one oxygen atom. Because of a cool effect called resonance, it gets to be shared across both oxygen atoms. It's delocalized. By spreading out that charge, it makes the solo dancer incredibly stable. And a more stable product means the reaction is way more likely to happen in the first place. And this just brings us right back to our main idea. We didn't need to memorize a whole new set of rules for carboxylic acids. We just applied the same fundamental principles we started with. Electrons move to find stability. It really is that simple. The rules are always the same. It's just a different dance. So when you start to think of organic chemistry this way, not as a terrifying list of facts, but as a simple set of principles for a dance, it totally changes the game. It stops being about memorization and starts being about prediction, about creativity. You now understand the core logic of how these molecules are going to behave. So the only real question left is, now that you know the steps, what dance will you create?